All right, thanks everyone. So this week I'll be talking about Cosmos 2.5. So there's been multiple different iterations of this model. Started with one and then they had two and now they're on 2.5. And so I'll talk a little bit about the history of the previous models, but most of the focus will be on what's this new model, what problem does it solve, um, where did this come from, basically. So the big problem that this paper is trying to solve is extracting information from documents is very difficult. So there's a few key kind of problems with that. The typical pipeline that a lot of people use is they will apply some OCR model to a page, and then that extracts out the bounding boxes of where the text was, and then also what was inside of those bounding boxes. Um, and so those systems have gotten very good. Like you can go to Google Document or various other places and you can pass a page into there and then it will output some text for you. But the big difficulty with that is often it doesn't come out in a good format in terms of layout. So like if you have a table or a chart or if you have something that's slightly skewed, it will cause all kinds of problems in terms of the actual format of the text that's output. And so if you try to pass that to an LLM, the LLM is going to choke on it because it doesn't understand the ordering of the tokens and the layout of the tokens. If you have a table header, it might not be lined up correctly, and then the model's not going to understand, like, this is a column of text, for example. Um, and so this is a very difficult problem that people have attacked in a bunch of different ways. Some of them doing piles of models, some of them doing end to end. Let's just train a model to do everything that we want. And so this is one of those more end to end approaches. Um, One of the big difficulties with documents specifically is that the resolution is typically so high, and you need it to be high in order to capture all of the words. So if you have a little image, like a ImageNet and all of those different data sets, they're actually fairly low resolution. So a lot of people would train on something that's like 224 by 224, but that's just not reasonable to do with documents because you need to see all of the fine-grained little details in order to read the text. So even just your standard 8.5 by 11 document, if you scan it in at 300 DPI, that's 2.5K by 3K, which ends up being colossal in terms of images and what we typically pass into these image models. So you need to find some way in order to handle all of that or break it into smaller parts and figure out how you'll handle that. And so these new LLMs that everyone's using, the Llama, ChatGPT, all of that stuff, they're extremely powerful in terms of their text understanding. But if they don't get the correct input representation, like if you lay it out perfectly so that the table actually gets represented as a table, then it can make it so that even though they're extremely powerful models, they just don't understand what you're giving it. And so one of the solutions there is to actually give it the image and then it's able to look at the layout and what's going on in the image to try to figure out um, what exactly you want from it. So the solution that they came up with, so this is actually a paper from Microsoft, is to make a multimodal model. And so this takes in image and text input, and then can do various things with it. So the way that they train this model is it's taught two things kind of simultaneously. And so imagine you give the model this image and then you give it a prompt, and one of the prompts is saying basically output layout information, and another prompt is saying output markup. And so this is what it would kind of look like out of the model. So this is what you take in, this is what you get out, and it can do it in these two different formats. And so one of them is trying to be layout preserving, so it tries to extract lines of text and then the bounding box that corresponds to them. And then the other one is trying to output it directly as markup. So you can see this one, like it directly made a table out of it in markup, whereas this one is just a bunch of bounding boxes and text. So this markup format is actually extremely favorable for LLMs because the LLMs have seen lots of markup and they understand what this means. screens, whereas this bounding box format gives you a lot of valuable information, but it's actually kind of difficult for an LLM to still understand this. But there's way more of this data out there than there is this data. So that's one of the big struggles. Um, so like I mentioned, one of the problems with these is having such a huge resolution and then also having different aspect ratios. So if you have an 8.5 by 11, that's a standard format. You could say make all of my documents that size or that resolution ratio. But the difficulty with that is you very likely have things that are all kinds of different orientations and aspect ratios and stuff. And so what people often do with images is they will end up just resizing it to fit whatever format they want. Um, and this is okay, but you end up losing a lot of information if you're stretching things vertically or horizontally. Then you're not getting the maximum information out of your context window that you can. And so what they figured out was they can basically scale the image just until it fills up the context and just be preserving of the aspect ratio. So on the right is what people would typically do is say, oh, we have this um, long and narrow document, and then we're going to map it to 8.5 by 11. And then you break it up into these squares, and each of these squares has like a very stretched representation. Whereas what they figured out is they say, okay, this is a little bit bigger than our model can handle, but let's just scale it down and then just take as many patches as we can that fills up the window. So you're not actually stretching anything, you're just scaling it to the right thing and then taking a bunch of tiles out of it until you pull out the maximum that you can. So this is the architecture of the
Hey, Ryan,
Cosmos. Yeah,
sorry. There's a question in the chat actually going back 2 slides. Just
sure.
can you explain more about the markup format?
Yeah. I actually have an example later here that might be informative. So here's an example of the two different formats that we have. This first one is the layout based one. So you can, it's probably pretty small, but you can see it's basically here's the XY coordinates of this specific line of text. And so this is what it would look like. Um, in terms of those bounding boxes that we saw. And then the markup format, it looks like what you would see on like a GitHub README or something like that. Um, so it has all of these kind of table formatting things, and you can say this is a header and this is a new row, new row, new row, and all of these split by the pipes are new columns. Yeah. Um, so in terms of the architecture, they actually inherited this from a model called Pix to Struct, and Pix to Struct was kind of solving a similar use case, but what they were doing was they were taking websites and their HTML and they were trying to go from like rendered HTML to the actual like underlying text and everything. Um, I think there's some small differences between markup and markdown. I saw them both of them mentioned in the paper, so I don't know exactly the specifics of what differs between them, but I think they're pretty interoperable. Um, but this Pix Destruct model was mainly focused on web pages, and they were able to get it to understand web pages really well. And then you can take this model and you can fine tune it for all kinds of different web understanding tasks or document understanding tasks. And so they borrowed this architecture and they just kind of gave it a different pre-training task. And um, they also trained it on way more data. Um, so basically, the input here is you give it some sort of image, and then it goes into the vision encoder, and there's a resampling layer that just kind of condenses this down to be less tokens, and then you pass it into something that's more akin to like our standard transformer, large language model type stuff, but it's relatively small. It's like on the scale of the original like BERT or GPT-2 or something like that. It's not some massive billions of parameters. The whole thing, the whole package, the encoder and the decoder is only 1.3 billion parameters. So in modern terms, it's relatively small. And then based on the prompt token that you give it, so you get the image tokens from the vision encoder, and then you have a prompt token that just tells the model basically, I want you to extract it in this way, or I want you to extract it in the other way. And then with that, it's able to output in the layout format or the markup markdown version. And both of these capture slightly different things. Um, so one of the important things with this, both of these graphs are actually from the Pix to struct model, but it's important to understand how these things kind of interact. Um, is one of them is looking at what's the actual advantage of this technique that they've done where it preserves the aspect ratio. So one strategy is if you just pad it to always be the correct aspect ratio and then crush it down, then you get this result. And so this is training steps on the x-axis. So you can see even after 30K training steps, it's significantly worse than the other ones. The other one is just directly stretching it, so not worrying about padding at all. You just stretch it to whatever your target resolution is. And then the other one, their current one is this variable resolution. So saying I'm just going to scale it up until it's the correct number of tokens in order to fill out the visual context. And so this turns out to be valuable. It gets you extra performance. And then the other thing that they studied in the Pixastruct paper that this one is inheriting from is seeing how much value you get from these more number of tokens. So the way that this model works is you take your image and then you break it into 16 by 16 patches, and then you see how many of those patches you can fit into a given context length. So they're showing basically if I have 1024 16 by 16 patches, I'm able to get this performance out. If I do 2048, then I get this performance out. If I get 4096, then I get that performance out. And so the Cosmos model was trained on 2048, which if you look at it ends up being like 724 by 724 resolution square if you were to just always have a square uh, resolution, which is not really that huge, but it's still quite a lot. So you can see that you can extend it even further, but it's at the cost of a lot of throughput. So this graph on the right is showing basically as we scale the resolution that you're taking in, how does the throughput change? And so you can see that if you go 512 to 1024 to 2048 to 4096, it gets significantly slower. So you go from being able to do like 200 images a second down to like 50. And so the cost is quite high when you're um, scaling things up to more pixels. But this is necessary to do because you have this performance curve where if you do things too small, then you just can't even pick up the text that's on the page. So one of the biggest things with this paper was the data that got trained again. So this is the same with all of the large language models. Um, if you put more data through it, then you get more performance, and that's kind of one of the big uh, things with this Cosmos 2.5. The original Pixdestruct was only trained on a handful of web pages, and this one is like to a colossal scale, basically. So they took a bunch of text from the IIT CDIP data set. And so the backstory on this is I forget which company, but some tobacco company got sued or something, and they had to basically make all of their documents public. And so this is a document set that's been around since like the 80s or 90s or something like that, but it's one of the biggest publicly available document sets. So a lot of the document papers are trained against this basically. And what they do with that is they take all of these millions of pages of scans and then they pass it through their Microsoft OCR system. And that gives them the bounding boxes and the text that was in those bounding boxes. And then they can go and retrain this model to kind of mimic their OCR system on these millions of pages. Um, and then the next data set is the archive papers. And so this is something that is easier that they can just basically download and it already has the text in the correct format so they don't have to rerun OCR or anything on it. And then they also pulled millions of pages of PowerPoint slides just out of Common Crawl. So they were able to extract this out. And that's the same thing. They already have the bounding boxes and the text and all of the layout information. So that's something easy that they can just pull from. And then they pulled 100 million plus from Common Crawl as well. So they just went through the entire web repository basically, and they found everything that had a PDF on it. And then they were able to extract this with PyMu PDF, which is just a PDF parsing library. So they didn't have to do OCR or anything. They just extracted the text directly that was embedded in the documents. Um, and then, like Pix to Struct, they also took a bunch of web screenshots. So they took a bunch of HTML, they rendered it out to a certain resolution, and then they said extract out the text that was originally in those web pages again. Um, and then they pulled a bunch of README markdown files. They pulled a bunch of just doc files, LaTeX, HTML, and so these ones. It's easy to just find these throughout the web. So they scraped a bunch of those as well. So they have this gigantic pool of 324 million pages. And so it's kind of difficult to compare against other like LLM data sets because people always measure that in tokens. But yeah, it's a very, very large data set. So if other people are training on a trillion tokens, this is probably uh, beyond that scale. Um, so one of the things that they did is they compared this against Google's commercial document OCR. So they passed these documents through the Google's OCR API, and then they said, how does Cosmos do in comparison to that? And so they compared it against a few kind of standard benchmark data sets, and they showed that even though this model it's kind of taught for OCR. It's not explicitly an OCR model. It's more of a kind of multimodal LLM. It's able to output this stuff like an entire page at a time in great format with very high OCR accuracy. So that's very, very valuable to say I can take the entire pipeline and now it's just in one model and it gives us a great format to be used by LLMs. And you're not going to take any hit in terms of like OCR performance. It's not going to get a bunch of characters wrong. It's not going to um, make errors in that way. So this is a very interesting model just because like if you want to input this to some other LLM, it can get you a fantastic uh, output format in just a single model. You just apply this to whatever you want, and then it will get you something that's very strong, actually. So here's some examples of the output that it can produce. So on the left, here's the input, and then on the right, here's the layout based um, prompt output. So you can see it gets text lines and it gets all of these little bits here, all of the numbers on the side, and is able to correctly locate and find the text and understand what it is. So this is really powerful that it's able to pick all of this stuff up in a very complex document in a single model. Um, so here's what I showed earlier. So this is what the output actually looks like. So it would be like here's X1, Y1, X2, Y2. And so that's saying here's the bounding box where that text occurred. And then here's the text that we actually found from the document. And so here's all the different text lines. Um, so this is a useful format because then you can go back to this and you can kind of re-render the whole page and see what it looked like. Um, And then here's what the markdown format looks like. And this is kind of more useful for actually passing to an LLM because it will group things together that are related, and it will also completely understand a table and stuff like that. Because that's one of the biggest challenges with a lot of these things. A bunch of people have been doing um, stuff with RAG, and one of the difficulties there is that you're very often chunking up your text into smaller parts, and then if you have your chunks in the wrong place, then you'll get a table that is missing its header, or a chart that only has one of the axes, or all kinds of stuff like that. And so this is a really great format because it's able to actually give you something that's kind of like logically oriented that can be consumed by a bunch of other stuff. Um, so this is all I have in terms of slides, but I wanted to show um, one of these, the Cosmo 2, because the Cosmo 2 is actually really interesting as well. So this one isn't as document focused. It was all focused on images and grounding. And so the import input format on this was really interesting, I thought. Um, so you can do things in all kinds of different formats. So you can say give an image and then ask a question of that image. And that's kind of a common multimodal thing. But then even beyond that, you can draw bounding boxes of specific things and ask questions of that specific thing. So it's given the whole image, but then it's also given like, here's a bounding box of something that I want to ask a question about. So you can say like the coach, but then the coach is actually something that you highlight and say like, here's the coach. Respond to the question about this thing. And so you can even do multiple bounding boxes. So this one is saying like, um, and it can do it on the input and the output. Um, they can like the model itself can output a bounding box and say like I was looking at this thing and here's this and here's that. So I thought it was interesting how flexible this format is that it can do bounding boxes in and bounding boxes out as well. Um, Catching up on questions. So their task specific prompt is just a generic
Yeah, that's what I was trying
it's
to understand, Ryan. Is it a simple one or is it a more complicated one?
it's nothing fancy. It's literally just a single token saying do this behavior or do that behavior. So it's a single token. It's not actually like a string of text saying operate in this way, but it's been trained in essentially two modes, and this is just kind of its switch to say which mode do you want me to operate in.
Oh, even though the original document can be very complex, right? Could have multiple paragraphs, could have images, could have text within images, doesn't matter.
Yeah, it's supposed to be generic to basically say if you're given this prompt, then output in this format. If you're given this prompt, then output in that format. So it's just a single token. It's not anything more complicated than that.
Interesting. Thank you.
There's a question about if it's truly a language model. Um, I think that depends on your definition. It does need to understand the spatial relationships and the surrounding language. It's not strictly a language model, but it is exactly the same transformers architecture that you would use in all of those models. So in the Pix-to-Struct paper, they actually trained it in a slightly different way, where they were masking out words and they were saying recover out the words that we masked out. And so in that way, it's a bit more language model-like. In this one, it's basically just a very souped up OCR model. So it's not truly a language model, but it's in architecture, it is like exactly the same as every other multimodal LLM. It's just trained in this specific way. There's a question about if it's open source, so it's not open source, unfortunately. It got released in September, and Cosmos 2 is up on Hugging Face and it's open source, but Cosmos 2.5 isn't open source yet. So it doesn't actually output images. So in the Cosmo 2 example, what it's outputting is bounding boxes. So if it outputs some text, it can output the snowman, and then it can say, here's X1, X2, Y1, Y2, and tell you specifically what it's looking at. So how it outputs the graph. Um, so in this one, it's not actually outputting the contents of the lines. It can probably see them, but it was not trained to do anything with these. It's only trained to pick up all of the text around it. So the model can see them, but it wasn't taught anything to understand these curves or anything. It's just purely focused on the text.
Hey Ryan, just to be
Yeah.
clear, basically what you have here on B on the right is they took a photograph of the original image and then they took the bounding boxes that were from the model and overlaid it. But the model did not output what we see. The model
Yeah.
just output text that has XY coordinates and the text contents of the boxes.
Yeah. The model output this. This is what the model actually output. That's just that overlaid on the original image. Yeah.
Can I ask a follow-up question to this? So then if you wanted to actually convert this to a human readable format, do you need to do some math and read these coordinates left to right? Like there's some logic here, right? That needs to be done to actually make this readable.
You could plot this back on the original pages. So there's a bunch of libraries that can help you do that. Say render this back to the original coordinate system, and then it would lay all the text out again. Um, but in reality, like people typically do like back to this where they say, okay, give the original image and just overlay it. And then in a UI or something, you might highlight over this and then see what the model actually output.
Oh, what
This
if I
is
just
a
want?
rectangular coordinates. Each
Yeah.
rectangle is denoted by two opposite vertices on one diagonal. It is enough to determine a rectangle. So they have only 2 points for each rectangle.
I'm just saying if you wanted to convert this to a Word document that you wanted to actually read, instead of looking at coordinates, you need to process this with some logic.
So the more readable format is this markup one. So this you could actually just directly say plug this in some markup reader and then you can actually read it. But you are losing information still. So like it's the same comment with this one. Like you would have all of the text correctly laid out, but then you wouldn't be able to actually see the graph and stuff like that. So the two different formats, like this one is useful but not readable, and this one is much more readable and probably also much more compatible with the actual LLMs that you might pass this into.
Yeah, I think it's kind of cool, Ryan, the way that the layout one sort of preserves I'm gonna say geography. I'm not coming up with the right word, but it's preserving that, whereas the markup markdown one is preserving semantic meaning. Like it knows, oh, this is a title, so this is a bigger, bolder font. It's not necessarily going to give you the exact same font, the exact same size, but it's still preserving the idea of here's a title, here's a subtitle, here's bullets, a table, or whatever. And so it's preserving that semantic information. So clearly, if it knows both of them, there's things you can do. But then also, I think some people are asking questions. Oftentimes, probably you want to pass the output of this into some other system. It's not quite like meant to be the be all end all final product.
Yeah, it's a very powerful get a good input representation for other models is ultimately what it's aligned for. And it could probably be well fine-tuned for a lot of tasks. So if you wanted to train it to do some other document thing, it would be very valuable. But yeah, I mean, out of the box, it's just like a very, very good OCR system, basically. Um, and so I pulled up this page, and this is kind of what I was talking about a second ago. So like one way to represent this is with those bounding boxes, you can overlay them back on the original, and then you can have something where you can like hover it and say, what did the model pick up out of that text? And then the other way is sort of like, let's re-render the whole page with the text that we pulled out of things. So like it shows this shows the original page, but what we were able to find out of it. So the bounding boxes and the text. There's a question about cleaning the output data. Um, I'm not sure exactly what that would mean in this context. They did a whole bunch of cleaning of the data on the training side. So they had those 300 million pages, but that was actually a subset of everything. So they did a whole bunch of stuff in terms of deduplicating it and cleaning it. So it was only the English. And then they also did a hashing step to make sure that it was um, not not duplicates and also beyond a certain quality. They didn't want bad quality documents ended up getting in there. And then they had whole sections on each of the different data types because they had to handle things differently in terms of how they got the OCR, how they got the parse text, how they went from web page to image and then back to text and get the spatial layout of that. So this is we were talking about recreating this at our company because it's a very valuable model and it's not open sourced yet. But the biggest thing is actually the data prep probably and not actually the training. It's just you have to go and gather 300 million pages and then you have to do all of these extra processing steps. Um,
I mean, when we get in the data, we don't have graphs, but we have like numbers on the axis, right? So we don't need them. We can like remove them, or I don't know.
Yeah, yeah. It's something that could be done, but it wasn't necessarily done in the paper. They just tried to give it as it was.
All right,
There's
if
a
you're uh,
there's a question about non-English words. So yeah, this is focused just purely on English, but it has the full vocabulary of a lot of these other language models, so it can output 50,000 different tokens. So in reality, it could probably do an okay job. It was probably exposed to a decent amount of non-English stuff, but yeah, the focus on this one was just English.
all right, so if you're okay, I'll transition and talk about the second paper, but we can still take questions at the end about either of the papers. So let me share my screen and fire this up. All right, so I actually have an old paper. This paper is about 4 years old, but two reasons kind of why I picked this. One is I saw a reference to this in something I was reading, and I I hadn't actually previously seen this paper, so I thought it was kind of interesting. And then also the last 2 weeks in um, in the book club, there have been some questions about generalization of neural networks and deep neural networks. And so I thought that this was a good tie-in to some of the discussions about um, how powerful deep neural networks at generalizing. So this paper, Understanding Generalization Through Visualizations, here. And so this is some research from the University of Maryland, and their idea was to look at some not super complicated neural networks. I mean, these are like small CNNs, you know, that they're playing with, and try to provide an intuition as to why maybe gradient descent generalizes so well. So in this paper, they're going to show that it's not because the problem is defined in a way that there's only one good minimum. Okay, so if you look at like if you're familiar with like linear regression, least squares, like there is only one global minimum, and so you can get there faster or slower, but pretty much any technique you use is going to give you the exact same answer. It should work. Okay. Um, and so then they get into a little bit about the geometry of the loss function, what those landscapes look like, and they talk about how high dimensionality often causes problems for us. There's sort of this curse of dimensionality, but in this case, they say it's a blessing of high dimensionality that the volume of these bad local minima is very small. It's actually very hard to find them. I'm not quite sure if it's that hard, but that's sort of the idea, and they have some nice visualizations to kind of go with it. So the problem we're talking about here is overfitting. Okay, so classical machine learning theory says that as you add parameters, then basically your model can memorize your training data and it can overfit and have poor generalization. Okay, so like I said on the overview, one hypothesis is it possible that there's something about the neural network architecture that it's just a beautiful architecture and it's not possible to overfit. And so they came up with what I thought was a very clever way to test this hypothesis. This is the main thing that I thought was really kind of fun and interesting about this paper. So so here is your standard cross entropy negative log likelihood loss. Okay, so you have a data set that's your training set, and that's this curly d sub t. This is your training set. Okay, and so if you have 1,000 training examples, then you basically sum up the loss from each example, and then you divide by 1,000 to get the average loss. Okay, so that's all that this function means. Okay, and so basically what we have here is we sort of take the likelihood that we're predicting the correct class, and then it's the negative log likelihood. So what they do with this normal loss function is they add a second term. Okay, so this part on the left, they changed this from 1 to 1 minus beta, and we'll get to the beta in a second, but this part on the left is unchanged, right? So if you just sort of look between these two slides, it's really unchanged. What they've done, though, is they've added a second term, and the only thing that's different about this term is instead of the negative of the likelihood here, what they do is they have 1 minus, so it's the reverse. Okay, and so instead of penalizing it when it gets the wrong class and rewarding it with 0 loss when it gets the right class, what it's doing is it's rewarding it anytime it gets the class wrong, and it's penalizing it anytime it gets the class right. But of course, if you did this on your training set, then these two would just sort of cancel out and you would get like no learning signal, right? It would just like flip a coin or something like that. But so what they do is this loss is actually calculated against a different set. So if you're familiar with like some of the contrastive learning techniques, you know, you often have like a batch and you would have like things that these are both dogs. So you want to have like low loss between them. And this is a dog and a cat. And so we want a high distance between these two. It's sort of the same idea. So basically they have two training sets, your normal training set, and then this second training set, which they call the poison training set. And there's nothing special about this, okay? This is just like a validation set or any other. But basically, when you pull a batch, what you want is you want on your regular training examples to classify everything right. And on this second batch, so to speak, that's pulled in parallel, you want to get everything wrong. All right. And then basically, instead of just having constants, they have this 1 minus beta and this beta over here, which allows them to change the weighting between these two terms. So when beta is 0, the whole second term on the right gets zeroed out, and you just have your normal cross entropy loss. Okay. And as beta gets bigger and bigger, approaching 1, then that means that you just have this really, really, your loss function is almost all based on getting the parallel Poisson examples wrong, and the training examples get so far downweighted. So there's a question: is there only any overlap? So these are not identical examples, but they're pulled from the same training set. So you imagine like CFAR, has like 10 different classes of images. I don't even remember, trucks, planes, whatever. So you're going to have the same classes. You're going to have trucks and planes, whatever. They're just going to be different trucks and planes. And in theory, yeah. So you do want different examples here. They're not the exact same examples, but they're from the same distribution. So they tried this on the Swiss roll problem. If you're familiar with that, it's 2 spirals. So there's only 2 classes, binary classification. But Swiss roll is hard for smaller, simpler models to do because they're not linearly separable. The spirals, sort of intertwine. And in this diagram, the red dots, okay, show the different points for this simple, I don't even remember, it was CNN or it was a MLP or what it was, but this small simple model, it started with random weights over here, and then as they trained it, it gradually followed this path over here, and then of course there's whatever hundreds, thousands of weights here, and so this is a t-SNE visualization in 2 dimensions. All right, now I don't love t-SNE, but it's good enough for the purposes for this particular diagram. Now, the other thing that they did is they said, well, every so often, let me take a checkpoint from this training, and I'm going to resume training, but instead of using the regular loss function, I'm going to use this function with the second term, with the Poisson term, okay? And I'm going to train it till convergence. So when they do that, they wind up on these various blue dots over here on the diagram. And again, t-SNE, take it with a grain of salt, but the idea is that there are lots and lots and lots of minima that they found using the Poisson loss. Now, I just want to emphasize one thing, which is that at first I was like, okay, well, but the Poisson loss function is different. So you're finding kind of a different local minimum. But the thing to understand, it took me a moment to think about this, is once you find one of these blue points, the model basically gets 0 training loss on both the regular cross-entropy term and the Poisson term. It's basically 0 loss altogether. So once you found one of these blue points, if at that point you resume training with regular loss function, it's not going to go anywhere. It's in a local minimum. It's in a happy local minimum. So the idea here is they basically prove there are lots and lots of local minima, not just the ones that SGD or whatever your optimizer, you could be using Armis prop, Atom, whatever, but that your algorithm is finding its way towards a local minimum, and these are different local minima that it has converged on, and they all have like 0 training loss. But what we'll see is that these blue dots generalize to our held out test set much, much worse than the destination of our actual gradient descent. So does this concept make sense? Any questions about just this idea of a poisoned loss function by using an extra training set, and the idea that we can go ahead and train to convergence, and that this is a local minimum for both the poisoned loss and the original loss, the regular loss.
So they, in essence, declare some random subsets as outliers on which we should not train, something like this?
It's not really an outlier in the sense that it's an inlier, but they purposefully reward bad performance on inliers. Okay,
So
so I'll give you a visualization in a second so you can see.
so it gives like better picture of all spaces that we have right there. It's like gives additional local minimums which we can see. So it's better understanding the whole.
Yes.
Yeah.
Yes. So this is showing, and again, this is just in 2D, but in 2D, our loss function our standard loss function has lots and lots of local minima, but these blue ones are not visited by our SGD. Only the red ones are visited by SGD. And so there's kind of a question of, well, if there's all these other minima out there. So one hypothesis was, is this neural network somehow like incapable of finding bad solutions? And the answer is no. It's definitely capable. There are bad solutions out there. It's capable of finding them, but when we do it the vanilla way, it doesn't. So the question then is, why doesn't it find the bad ones? These other local minima are stable. If you go and you pick one of these and you give it the regular loss, if you give it as your starting point and you train on it, it'll just sit there and be perfectly happy. Well, okay, depends on your definition of stable. If you're fully in the local minimum, it is a local minimum and it is stable. But what we're going to see is that it is a much narrower, smaller local minimum. And so in that sense, it's a little bit harder to find or stay in that minimum. That's the gist of it. So one of the things they did is they said, okay, maybe it's because we used SGD, maybe it's whatever. So they tried all sorts of optimizers, right? Regular SGD, Atom, RMS prop. They used LBFGS, which if you're familiar with is a second order solver. And then they also used this thing called ProxPop that I'm not familiar with, but they said this thing doesn't even use gradients in order to iteratively find a solution. So they're saying like, here's a good example of something. It's not even sort of a function of the gradient, okay, for this. And all of these converged and generalized well. So they said, okay, so if it's not the neural network architecture, and if it's not the particular optimizer algorithm we're using for gradient descent, then our new hypothesis may be something about the geometry of the loss function is what's helping us with generalization. So the analogy they give is that in a support vector machine, we have this idea that a wide margin indicates good separability of classes. This is highly desirable. And so then they draw a connection between sort of the flatness, the wideness of a local minima in a neural network loss landscape is a lot like a wide margin in SVM, and that we want flat, broad bottoms to our minimum. We don't want sharp, narrow, pointy minima, because with the sharp minima, if you're a small distance away, it's going to lead to a much, much worse loss. So this ties to the question in the chat about stable. So they're stable in the sense that once you get to the bottom of them, you really are in a minimum. We'll see a visualization, okay? But they're not as stable in the sense that if you perturb it a little bit, all of a sudden you get very different predictions and you get very different loss. So let's take a look at a picture. So here's our Swiss roll. You may have a little bit hard time telling, but this is class 1, the red dots, this spiral. And this is class 2, the blue dots, this spiral, okay? So if you train with vanilla SGD, you get a decision boundary that looks kind of like the blue and the red regions here, okay? And so you can see that there's kind of a wide margin between where the red dots are and the decision boundary. And there's kind of a wide margin between where the blue dots are and the decision boundary. If they crank up this beta factor for their poison loss, they can get it so that this network has 100% accuracy on the training set on both the real training set and the poison training set. It gets 100% zero loss. But it has terrible, terrible performance. It gets 7% on the test set. It's binary classification. So 7% is much, much worse than 50%. It's much, much worse than random. And you can't even really see accurately in the picture on the right. But basically, you'll notice that the decision boundary for all the red dots, most of them are like completely surrounded by blue, and there's like a teeny island of red that you can barely even see in some cases. So like here on the left, you can see, oh, okay, they're sort of near this like red area. But for a lot of these over here, it's like the red decision area is so tiny that you can't even see it. It's just basically this minuscule island surrounding the red dot, which of course means that if you perturb it even slightly, it's now predicting blue instead of red, right? What you would think is that you would want a model to generalize if you interpolated between two red dots that you would also predict red. That's like the most simple generalization possible. And so they've sort of trained this model so that it's actually doing the reverse. And then the same thing with the blue dots. If you look at them, you'll see most of them are like completely surrounded by red. Every now and then you see like this little tiny peninsula of blue that'll like peek out to where the point is, but a lot of them you can't even tell. They look like they're just in a sea of red. So the cool thing is this is what the decision boundary looks like, but it's very difficult to picture decision boundaries once you get past 2 dimensions, possibly 3 dimensions. So there's a technique you can use to visualize the loss landscape, okay? And so just trust the authors, trust me, that these 2 pictures at the bottom are normalized. So obviously if you zoomed in on this narrow thing, it would look wider, okay? But they're normalized so that they're on similar scales. And so what you can see is that you have a much wider local minimum here with a flatter bottom, whereas on the right here, we've got this tiny little point where we get 100% training performance. But if we move ever so slightly off of that, then our performance decreases dramatically. So in terms of visualizing the loss landscape, this is a paper. I don't know if you guys have seen this, pretty well known. So it's called Visualizing the Loss Landscape of Neural Nets, came out in 2017. And they do very cool work. And so this is an example of a CNN with no skip connections. And on the right, this is a ResNet that has skip connections. And so you can see a dramatic difference in both how smooth the contours are and how wide the local minimum is for what it got trained on. So that's the technique. I'll have links at the end here. So if we're looking at how wide that sort of hole is for the local minimum of the basin, right? Then you can kind of you might measure it different ways in terms of like how do you define like the width or the height of a basin. Like it depends on like how high up you go. And so you'll see that they can say, regardless of which metric we pick, how high we're going to go, we sort of get the same problem, the same properties. So in this case, they have this cutoff that they call 0.1. Again, not going to go into the gory details how they calculate it, but basically they show as they poison more and more. So again, poisoning on the far left is close to 0, none. And then over here, 1 would be 100% poisoning, okay? So as you poison more and more, then what happens is, again, you're always training to convergence, so you get 100% train performance. But in the red, this is your test performance. And you can get it to where it'll even drop below 50%, like we saw one that was like 7%. And if you compare, well, the different models that have different generalization gaps, different distance between train and test, how does the loss surface compare for these? You see this pattern where as your performance gets worse and worse, your basin gets skinnier and skinnier and pointier and pointier. That's basically what they're trying to show. So it's the same graph. On the left, it's our Swiss roll, which is a very, very small, simple problem. So this is only a 3,000 parameter model. On the right, this is street view housing numbers. And so they use a more regular small CNN. It's got 300,000 parameters. It's the same property. And then here's the thing is that they say in high dimensions, volume is very, very sensitive to small changes. So when something is narrower, the volume of that region drops dramatically, many, many orders of magnitude. Okay. So on the left, this is the Swiss roll. And again, these different cutoffs are basically how high up the basin do you go in order to calculate volume. All right. So they're saying it's not because they cherry picked some special way of calculating it. Even if they had picked many different, they have the same property where when the generalization gap is low because they have no poisoning, then the volume is much higher. When the generalization gap is large, the volume shrinks by a ton because these are negative numbers. And so if you read these, this is the log base 10 of the volume. So if something goes from negative 7,000 to negative 15,000, that means that the volume is 10 to the 7,500 power smaller. So it's not 7,000 times less volume. It's 10 to the 7,000 less volume. I don't even know what that number is. It's astronomically huge. And so then for the street view housing numbers, you get this crazy stuff where it's like 10 to the whatever, 150,000 times smaller volume from the top to the bottom of the scale. So that's the general idea here, that this is pretty much the end of the paper, just saying like, you can imagine that it's very hard for SGD to find some of these local minima if it's just sort of, wandering around because you're taking step sizes. And so unless your step is like really, really, really close to that particular local minima, you're just going to miss it altogether because you're going to, even if you were, going along it, you would go right past it to the other side of that local. Here's more visualizations. So we saw 2 examples before. So now this is 6 examples. So you can start with normal. And then if you do just a little bit of poisoning, you can see this decision boundary starts to get less smooth and the points get closer to the boundaries. And you keep going until you get this really horrible, ugly decision boundary where, again, at first blush, it looks like all the blue points are actually inside the red decision boundary. You just can't see these tiny little islands of blue. One last slide. So they said, is this always true? And so here's an example where you have a circle of blue dots surrounded by 2 circles of red dots. So you have the outer circle, which we're not going to do anything with. And then you have this inner circle. So on the left, if you train a neural network, it'll have no problem. It'll give you a decision boundary that looks like this. And you'll see the decision boundary is like about as far away as it can be from each of the blue and the red dots. If you move these red dots into a bigger circle such that they get closer to the blue dots, it makes it much harder for the neural network. And so I don't know if you can see, but these red dots are pretty close to the blue, but not that close. And so the model's sort of barely able to solve the problem. And it has this somewhat tortured looking skinny decision boundary that connects all of the red dots. And then if they move the red dots even a little bit closer to the blue dots, then actually the model is unable to do it, and it has this horrible thing, and it doesn't actually get 100% training accuracy. So in conclusion, right, they analyze these highly overparameterized neural networks. And the part that I liked about this is they designed this principled Poisson loss, which finds local minima that are local minima for the regular loss, but they don't generalize well. And so then you can see that sharp, narrow minima have much, much, much smaller volume. And the idea is that it's much harder for, remember, SGD is not continuous. It's taking discrete steps, right? It's very much harder for you to be in sort of the attraction basin of a minimum when it's that much smaller. So since this, much, much more research on generalization has happened, there's other things. There's another interesting result on mode connectivity. still a lot of unanswered questions, but since we were kind of talking about generalization, I thought I liked this little poisoning technique, thought it's some good visualizations. And so then here's the paper. And they also have a YouTube video, which is just a short little, like, 20-second video where you can see they pick a loss and then they perturb it just a little bit and the performance drops dramatically. The second link is the Visualizing Lost Landscapes paper. And then there's a website, lostlandscape.com, if you want to see some beautiful pictures. And then this is the other paper, the mode connectivity paper. And so there's some cool stuff you look at. And if nothing else, not only is it like cool in terms of the ML, but it's actually like pretty pictures. So this is the Lost Landscapes website, and they just have some really fun, cool pictures on here. This is the mode connectivity paper, and they have a blog, and you can see this is sort of a three-dimensional look at, like, there's a minimum over here, there's a minimum down there you can't see, and you can see sort of there's this channel that kind of connects them, which is the main concept of this paper. And so then this is just a more 2D, whatever, conceptual drawing showing that, hey, we've got these minima, and there actually is a path connecting them where the loss is very similar. So that's a whole separate subject in terms of, like, whether or not SGD can kind of wander around these low basins from one minima to another until it finds sort of the best possible of the similar. But I just thought, like, some of these pictures are just really freaking cool looking. So thought that'd also be fun to share. All right. So there's a question in the chat. I kind of waited till I finished this. Is to summarize, like, is it that there's somehow regularization happening in neural nets? And so the people had talked about this implicit regularization. That's sort of the term that people coined. I think what the authors of this paper are saying is it's not really regularization in the sense that you're constraining the model in some way. What it's saying is that the lost landscape is like, you know, this surface that has these minuscule, tiny little holes in it, and you don't really have to worry about falling into one of those holes if they're that tiny, right? The likelihood that you step into one of them is just like really, really, really small. And so that's really the idea there. So, like, if you were on the moon and you have these big craters, like, the odds that you find yourself in a crater, it's pretty high because there's big honking craters. Some of them are miles wide, right? But if you have a crater that's like the diameter of a dime, it's 1 centimeter, then the odds if you just, like, pick one point of being inside of one of those craters is actually much, much, much smaller. That's the general gist. All right, cool. So I think we'll pause here, and then we can open up for questions on either paper and then shift gears. We do have the office hours for just general ML questions. Ryan, you want to stop the recording?
Sure.